So what better than an introduction by your students? So thanks, Emmett, for setting the stage. And I'm a professor here at Stanford, so I like to test people. So I want to start testing you whether you paid attention to the previous presentation. So I put here a collection of images, and I want to ask you, what do you think there is in common between all these different images? So we have a car, a soap bubble, a plastic bottle, pharmaceuticals, myself a few years ago, a cornfield, and actually an enzyme. What do you think all these things have in common, given the previous presentation? So we're going to be talking about the importance of ... Exactly. So that's catalysis, okay? So because catalysis is involved in all these processes. So we are making materials based on catalysis. So 90% of any material around us, so 9 of 10 objects around us are made through at least one catalytic step. So we make detergents, we make plastics, we make pharmaceuticals, we make cars. We also make gasoline to power your car. But catalysis is also what nature relies on. So those cornfields can grow well because they rely on enzymes that do a lot of catalytic transformations and provide molecules. And probably you also learned from the previous presentation that catalysis relies on surfaces. So we need to make these surfaces very active by making them very, very small. So in our group, what we try to do is to engineer materials at a very small scale of atoms and molecules and try to make nanostructured materials with high precision. And what I mean with that is exemplified in some of these microscopy images that show not atoms, so all of those dots, although those dark dots are not atoms, but those are particles containing thousands of atoms. But nowadays, with nanotechnology, we can make these molecules with very high precision, so we can bring together a very precise number of atoms in order to make these well-defined structures. And then we use these well-defined structures for catalytic processes that hopefully will run and will be very active, stable, and selective. So the first question, some of the research that we do in our group is, first of all, how do we make these well-defined materials? Because it's not that easy. So we rely on techniques and on collaborations up at SLAC. So this is Liang Wu is a postdoc working on this project, and Krista Sone is our collaborator at SLAC, to use SSRL, the synchrotron, in order to understand how these materials grow. And here there are some curves that are not as important now to understand what they are. Those are essentially telling us how our materials developed in the solution. And what we can find, for example, is that if we want to make these well-defined materials, we have to mix appropriate components. And when we mix these components, we can also find surprising things. We can, for example, find that these materials form some small particles, some small nanocrystals, and then these nanocrystals self-assemble into crystals of nanocrystals. And this is something interesting that we found a few months ago, and that would tell us how to make these better defined materials that we can use for catalysis. Then once we know how to make these materials, we use them for catalytic applications such as emissions control, and you heard that from Emmett's talk just a few minutes ago. For example, we're looking at how to limit emissions of methane in the atmosphere. And in order to improve the materials, you can do a couple things. You can just screen random materials, and you hope to be able to win the lottery and find a material that works. Or you can do what we call a systematic screening. So you change one parameter at a time, and you understand how that parameter is affecting reactivity. So in this case, we prepared different nanocrystals based on palladium, because we know that palladium is very good for this reaction. And we add one additional promoter, which are different metals here, manganese, vanadium, iron, and so on and so forth. And then we segregate these two phases in a controllable way. And then we can screen this material and see that, for example, in this turnover frequency graph, you see some materials perform better than others. So we can understand how to improve these materials based on this systematic screening. But what I really want to talk about today is how do we get to the next generation of catalysts? Because if you look at catalytic materials, yes, they rely on small particles and everything happens on the surface. But what enzymes do in nature to be so extremely selective and produce the molecules that we need are to have very small pockets there are three-dimensional pockets where the magic happens. So we want to make the magic happen as well. And when you look at our materials, the spice mold, these are not three-dimensional materials. These are still surfaces. So if you look at conventional catalysts, for example, these are based on small particles that are deposited onto a support. So we have what we call a two-dimensional type material. But in order to engineer that pocket, what we are developing in our group is what we call embedded catalyst, in which you put a third dimension and you confine your reactivity in that small pocket. And for example, you try to affect the selectivity and how to build molecules that you engineer in length and you engineer in functionality. So this is something that we started a couple years ago. Andrew Risco is a PhD student working on the project. And first of all, we started on polymer-based materials because polymers can be functionalized very easily and are analogs of enzymes. So this is what we call artificial enzymes. So for example, we deposit some of these nanoparticles that are catalytic centers on this polymeric material. So these are the black dots, are the nanoparticles supported on our polymer. Then we remove the ligands from the particles in order to activate the catalytic surfaces. And then we build this three-dimensional shell around the particles by putting more polymer around these materials. And here you can kind of see this overgrowth of the polymer around the particles. So here we think we are creating these artificial enzyme pockets where we are confining our surface reactivity to these pockets. Do they work well? First of all, they provide higher rates than conventional materials. So in green, you have the dots for this particular reaction, which is the oxidation of CO to CO2, which is used to remove CO, which is a toxic compound from streams. And these green dots have higher rates in turnover frequency compared to conventional materials. So by confining the reactivity in those pockets, we can get higher rates. And we can also get control over the transport of species, because you see those oscillations in reactivity that you see at increasing temperature means that we are changing the reactivity inside these pockets, and that CO2 is confined in the pockets, and it's changing the reactivity of the system, going from high activity state to a low reactivity state. And we can repeat this. These materials are very stable for many, many hours, and they show these CO2-induced oscillations that we hope we can use also to induce selectivity. Then if we want to further increase the stability of this system, what we can do is to take the first three steps as we did before. So we get these polymeric materials that we call POFs around our particles, but then we use a nanocasting technique in which we use to infiltrate these polymeric materials with inorganic materials such as silica in order to create materials that are way more stable even at higher temperatures and pressures. This is what Izulu Aidbekova is working on right now, and we hope to use these materials, for example, for transformations that are even more challenging, such as the conversion of CO2 to alkenes or the conversion of methane to other compounds. So with that, I hope I just gave you a brief flavor of what we do. We use these nanocrystals in order to understand, control, understand, and improve materials for catalytic transformations. We work on the activation of what we call small molecules, but that produce big challenges, such as the production of hydrogen, conversion of CO2 and methane, and the activation of nitrogen. If you are interested, please go visit our website, and I'll be happy to stick around a little bit longer after this session and talk to you. Thank you very much, and thanks for the opportunity to talk today.